As we study Bowen's reaction series, we have to start taking a look at what takes place within the Earth. And here we're going to look at one of the plate boundaries. We're going to look at a divergent boundary, where plates move apart and new oceanic lithosphere, or new oceanic crust, forms. So this animation is showing that liquid rock is coming from the inner part of the Earth. Let's just say it's actually the outer mantle, and these rise due to the buoyancy, right? Hot material rises, and it forms new young oceanic crust at divergent boundaries, and we call these ocean ridges. And you'll see that this side of the oceanic crust is moving this direction and this is moving this way. So divergence actually shows me an illustration in this animation that oceanic crust is, or these sides of the oceanic crust are moving away from each other. So a divergent boundary further illustrates that. So here's another animation. Here we have hot liquid rock that's moving from the inner parts of the Earth. Remember, inner parts of the Earth are going to have more iron concentrated. So we're looking at how ultramafic rock from inside the Earth is going to melt out only the mafic minerals that are going to rise. We call these rising plumes. We just call them the mafic, right? Basalt is going to then reach the Earth's surface and crystallize. So this animation should help kind of illustrate that. We have rising hot liquid rock. It actually forms at this area right here. It's actually called a fissure. This is where liquid rock reaches the Earth's surface at divergent boundaries. And this plate is moving this direction, and this plate is moving this direction. So once again, a further divergent boundary. That this rock is moving through the crust and upper mantle where it's solid. This is the lithosphere. And here we have this animation just further showing how and why these divergent boundaries form. This hot rock eventually thins it enough to where it eventually moves apart. And that's a form of divergence within the divergent boundaries itself. And here's one further animation, and I'm looking at these two pictures here. If I look at from the surface, this is a divergent boundary. Oceanic crust is moving this direction, and on this side of the boundary, it's moving in this direction. So let's look again, let's look at two dynamics moving on at the same time. If I look at a cross section here, hot rock, liquid rock is moving from the mantle. This is mafic in its composition. It rises, reaches the Earth's surface beneath the ocean, so we don't see it. But these are taking place all along the Earth at the same time. And we see this, and we have young, new mafic oceanic rock that's forming here at this location. And the process of divergent boundaries are taking place all along here where we see this plate boundaries map. All these lines right here. We have oceanic crust, young oceanic crust, creating new oceanic crust all over. Right? The planet is riddled with these, but it's covered by ocean, so we can't really see it. And they're not very volatile. They're not very, when we think of volcanism, we think of these massive explosions. Well, these are basaltic. These are low silica content, so they're very mild. So they're not newsmakers, but they're constantly happening. And this is what is driving plate tectonics. These are moving this direction, and this is moving this direction. And where I find this, I'm actually finding, or looking at this map here, I'm seeing divergent boundaries. The second plate boundary we're going to look at is called a convergent boundary. And this is where plates move towards each other. An oceanic crust, or lithosphere, is consumed. It's subducted. And so this here is going to be my picture of oceanic crust. Notice it's much thinner than continental crust. And it's much denser, though. It contains iron. And because of its mafic composition, when it comes into contact with the less dense felsic granitic composition of continental crust, it's going to subduct. It's going to subduct because it's denser. So as I run this, these are converging. This is my convergent boundary. And I want to pay attention over here. This is where we view partial melting. We have this subducting plate that's moving into the, let's just say, towards the interior of the Earth. It's heating up. And so we're going to melt out this partial melting. We're only going to be extracting the felsic minerals. And so this subduction of mafic oceanic crust, it's subducting beneath the continents. It's going to be generating this very felsic type of rock that's going to rise. This is liquid. It's going to have a buoyancy to it. It's going to be less dense than the surrounding rock, and it's going to rise. So here I can look at this picture a little bit more detailed. And so I have subduction of oceanic crust beneath continental crust. This is where they converge. This is a convergent boundary. That this is moving this direction, and I guess at some level that this continent is moving this direction. But they're no less colliding, so this is a collisional boundary. And what happens is that as it subducts, this mafic basalt is going to have what we call partial melting. the lighter minerals are going to be able to be extracted from basalt. So basalt's going to sweat out. It's literally going to be losing its felsic and even a few intermediate minerals of the intermediate variety. And these are going to melt out and they're going to rise. So if I run this animation, I'll be able to talk through it a little bit further. So here I have this partial melting taking place. Partial melting, very important. And I'm creating these felsic plumes. And I can actually create continental crust by observing subduction of oceanic crust. So here, once again, I'm subducting. This is emphasizing just this area at this location here. It's heating up. It's melting out the lower melting point minerals. Those are rising due to their buoyancy, right? Hot material rises just like hot air rises. Convection is a true statement. In this case here, we have the creation of continental crust due to the remelting or the partial melting of oceanic crust. And here I have one last animation of a convergent boundary just to drive it home. I have the oceanic crust that is subducting beneath the continents, continental crust. So I am forming granite by the partial or the remelting of oceanic crust. As it heats up, only the low melting point minerals that are felsic are going to be melted out of it. So you're literally extracting felsic minerals out of a mafic rock. They're there. They're just not in the form until they remelt, and it remelts and it becomes this liquid, and we separate it out. So the mafic denser materials are still going to continue subducting, where the felsic minerals are going to rise, and this is an area in which we will find volcanic activity. That concludes the animations on plate boundaries.